This is the third video of a series on vectors. The last video looked at adding vectors by diagram in head-to-tail addition, shown by this triangle here. So for adding vector u and vector v together, we go along vector u. At the head of vector u, we join the tail of vector v as if you're going on a journey. So you start here on the left, move along vector u, then move along vector v to finish here. If you join up the start and the finish, that's the resultant vector u plus v. So that was head-to-tail addition, as if you're going on a journey. Could you use that in this video on diagrams where we can add vectors together head to tail to simplify some vector additions. So here's a sample of vectors. There's vector A here, certain size, certain direction. Reverse the arrow, that's negative A, so vector negative A. Similarly for vectors B, C, D and E, the vector's there with its negative. So suppose I wanted to add some vectors together. Let's say I wanted to add vector A, vector C, vector D, and maybe vector negative E, and I wanted to add them together. I put them together as if I'm going on a journey, head to tail. There's various ways to put them together, but there's joining A and D together. There's A, C and D joined together. And there's negative E joined on. So this is like D plus A plus C subtract E. So this is adding negative E is subtract E. And if I'm going to add these together, I start at this end and I finish here. And it so happens in this case that if I take vector B and a second vector B, that takes me straight from start to finish. In other words, the resultant vector is 2b. So here it is in this diagram. I've added A and C and D together and subtracted E. Doesn't matter the order it's done. It happens to be D plus A plus C in the diagram. And then subtract E, but it can be done in any order. And the resultant's 2b. In other words, it simplifies to 2b. So that's head to tail addition, and that's the resultant vector in black, 2b. So here's a diagram of the kind of question you'll get if you click the link in the description. There's a worksheet as a PDF, it has answers with it, and it involves diagrams with vectors and simplifying the addition of some vectors. So this is identical, congruent parallelograms. There are 6 of them. This side here, AB, is a representative of vector V. So directed line segment AB is a representative of vector V, and directed line segment AE is a representative of vector U. Any other vector, same size and direction as AE, will also be vector U. So Fji is vector U, DH is vector U, EI there is vector U. Similarly, vector V. So there's vector V. So CD is vector V, JK is vector V, and so on. Same with our negatives. Reverse the arrow, that's negative U. So JF is negative U, HD is negative U. There's V with the arrow reversed, that's negative V now. So DC is negative V, JI is negative V, and so on. So what you have to do is express a directed line segment like GK using U and V. So you're looking to go from G to K. So you're able to spot G to K is exactly the same as A to E. It's vector U. So GK is vector U. Next one says FE, going from F to E. You should notice it's the reverse direction of V here. In other words, there's F to E, it's negative V. V with the arrow reversed. So FE is negative V. IL. So we're going from I to L. So there's I to J, and there's J to K, and there's K to L. It's 3 V's joined together to get from I to L. So IL is 3V, 3 times V. For AF, to get from A to F, well, to go from A to F, here's U, and there's a V joined on, and that takes you from A to F. It's a U plus a V. It wouldn't matter the root. It could be V plus U, which is the same as U plus V. Takes you from A to F. Next one says A to J. So there's vector U. Here's vector U again. That's 2 of them. And then a vector V, and I've gone from A to J. It's 2U plus V. Again, it would be the same answer regardless of the root. There's V plus 2U, which is the same thing. Next one says EB. So I want to go from E to B. So I can have vector V here, and then reverse the direction of U. That's negative U, and that's me going from E to B. V and negative U. Again, it wouldn't matter if I had negative U and added on V. So there's negative U plus V, but that's the same as V plus negative U, or V minus U would be the best way to write it. So finally, A to L, going from A up to L, well, there's vector U, there's another vector U, then right along the top here, and 2U plus 3V takes me from A to L. So that's the result, 2U plus 3V. So it's adding combinations of the vectors U and V, or their negatives. You can express every other directed line segment there. Now to show you AL can be got in different ways, 2U plus 3V regardless of root. There's AL's 2U plus 3V. There's the root we just had, 2U plus 3V. That takes from A to L. Lots of alternate roots. There's V followed by 2U followed by 2V. That is, there's 2 U's there and 3 V's. Same result, different root. Here's another root, V followed by U followed by V followed by U followed by V. Result, there are 2 U's and there are 3 V's. Doesn't matter what route you take, doesn't matter if you double back. Whatever route you go will always end up with the same answer, 2U plus 3V, which equally could be written 3V plus 2U. So that's one kind of question. This is a bit harder. So this is a hexagon. Regular hexagon means all the sides are equal, all the angles are equal. This side AB here, directed line segment AB, is a representative of vector U, and AF of vector V. So that's 2 vectors, U and V, and you have to express other sides, other directed line segments in terms of U and V. So say you wanted CD, from C to D. From C to D, there's C to D. It's exactly the same as vector V. So CD equals vector V. The next one says DE. So it wants DE from D to E. That one, D to E, is the reverse direction of U. So it's the same size but opposite direction to U. So that's DE is negative U. Next one says BE, how to get from B to E. And that's a bit trickier to spot. Is actually maybe possibility of 2 of these joined together. Here's a demonstration of how it can be shown to be that addition of two v's. This is a hexagon split into 6 equilateral triangles. The angle at the centre is 360 degrees. It's split into 6 equal parts, so each part is here 60 degrees. These two lines from the corner D to the centre and corner E to the centre, these two sides are equal, so it's an isosceles triangle, two equal angles at the base, so there must be 60 degrees each, so it's in fact an equilateral triangle, 3 equal angles, 3 equal sides. Since the 3 sides are equal, this line from the centre to E must be the same as from A to F, same size, it's going in the same direction. In other words, that is vector V. So if I get rid of the extra stuff here, that is vector V. Now equally, that is vector V there. So if I get rid of these parts there, that's 2V. BE is 2V. Now, that's quite tricky to get. It's because they're equilateral triangles, 3 equal sides, that line there was the same length as V. And so is that one. Now in the same way, that is also the same as U. And that's also U. So we can use that to answer other questions. So BE was 2V. Suppose we want AE to get from A to E. We must use U and V to get from A to E. We don't know what FE is at the moment. We could work it out. But to get from A to E, I can go along vector U. I can then go along BE here, which was 2V. And that's taken me from A to E. It's a U plus 2V. Equally, you could have it as 2V plus U. Now the route wouldn't matter. I could have gone that route. I could have gone V, then along U here, because that's this side here is parallel to that, and then along V. That's V, U, V. Same result, U plus 2V. So the route doesn't matter. And finally, the one that says AD, well, to get from A to D, A up to D, I can simply take the previous route, which was U and 2V, and then add on another U. There we are, up here. So that's given us U, 2V, U. In other words, 2U plus 2V. Now again, the route wouldn't matter. So there can be different routes. I mean, I could have gone along here and then up there. That is U plus V plus U plus V. It would still be 2U plus 2V. So that's using a hexagon that uses just internally there the 6 equilateral triangles, which meant 3 equal sides. And that basically meant, like, that's also vector U, that's also vector V, and you could use combinations of U and V inside the hexagon. And this last case, this kind of question. So we've got some vectors here, A, B, C, D, E. Want to simplify addition of some vectors like C plus D. So if you look at adding C and D together, there it is in the diagram. There's C followed by D. It just results in B. It starts here, goes along, up here, and it finishes at that point. It starts here, finishes here. That's just straight from start to finish is vector B. So C plus D is equivalent to B. The next one says B plus E. So you're adding B and E. There's B and there's E. They add head to tail. Starts here, finishes here. That's the same as A. The next one says EDC. So there's E. And there's D. And then it says C. There's C. Just put them together. Didn't put them together in the correct way as we're adding, because they actually add C, D, E. So although we had E plus D plus C, they actually add together C, D, then E. But that's given in the diagram. When you put in E, D, and C, you can see how they add together. They start here and they finish up there. So that's equivalent to A. So in that one, that was C, D, and E being added. It didn't matter, it said EDC. When you add them together, it doesn't matter the order. And that's equivalent to A. Next one says A minus E. That means take A and the negative of E. So if I put A on, and there's the negative of E, E with the arrow reversed, start here, finish here, it's equivalent to B. Now, E minus A is just that order reversed, so this should be negative B. So E minus A is E followed by negative A. There's E, and the negative of A is the arrow reversed. We're going the wrong way down B here. That is, it's negative B. That's E here, and negative of A starts here, finishes here. You go against the arrow of B, it's actually negative B. In other words, it's that. There's the negative of B. And this is B minus D. That's B plus negative D. So it's B, and against the arrow of D, the arrow is reversed for negative D, and it starts here and it finishes here. It's just C. And this is B minus C, B and negative C. So we put B, there's B, and there's a negative C with the arrow reversed. If you look at the start, it starts here at the beginning of negative C, moves along and then up. So it starts here, finishes here, that's equivalent to D. And this says D minus B plus A minus E. So you just put these on the diagram, D, B with the arrow reversed, A, and E with the arrow reversed. So there they are there. There's A, and there's D, but B and E had the arrow reversed. Now, you look for a journey, it starts here, goes up, down here, up here, and down again. It stopped here, this is where it finished. It started here, and it finished here. It's just D. So the answer to that is simply D. The part which was part which was negative B, and A and E was just a loop. It just cancelled out to 0. So it was equivalent to D. So that's examples that will be in the worksheet. If you click the link in the description. This worksheet was the worksheet for the first and second videos on 2D vectors. So that was for the first video on components and magnitude. That was the second video on adding and subtracting and multiplying by scalar. Questions 8, 9, 10 and 11 are all the type of question you've just seen. They're quite tricky. At the back will be the answers. There's also a set of notes that covers all the videos on vectors. So if you click the link in the description, you get the worksheet and the notes. The next video goes into 3 dimensions with coordinates and vectors. Hope you found this video